last few lectures we discuss what can be called elements of set theory. In fact, we took a review of some of the properties of sets. In this course, of course, we shall be dealing with many sets, and the most important of those sets is the set of all real numbers, okay, or also called real number system. So let us discuss a few things about this real number system in today's and a few more lectures. So the idea is now to discuss real number system. Okay. Now first important question here is that how does one define real numbers, or how does one construct this real number system? Well, there are many ways. One can start, I mentioned in one of the lectures earlier that set of all natural numbers can be constructed using what is called Peano axioms, okay, and once you construct a natural number, set of all natural numbers, then that natural numbers along with these operations of addition is what is called a semi group, okay, and there is a very standard way of constructing a group from semi group. So that leads to the set of all integers. Then again, algebraically speaking, the set of all integers is a ring. In fact, is something more than a ring, what is called an integral domain. You would have heard of these terms in algebra, and there is again a very standard method of constructing a field from an integral domain, okay. You define certain equivalence classes and define some operations on equivalence classes, and suppose you apply that method to the set of all integers, you get this field of rational numbers. The real question is, how do you go from rationals to reals, okay. There none of these algebraic methods work. Rational numbers is already a field, okay. There are two ways. One is, in fact, those two ways are due to two famous mathematicians. One is due to Dedekind, and the second name we have already heard, Cantor, okay. This procedure is what is called defining what is called Dedekind cuts, okay. Those are subsets of rational numbers satisfying some property, and using those Dedekind cuts define the real numbers. And the second approach, which is that of Cantor, is using the sequences of rational numbers and then define what is meant by, again define some equivalence classes of sequences of rational numbers and associate one real number to this. This first approach, Dedekind cut, you can find in Rudin's book. Rudin's book, first chapter is devoted to that, but we shall not go into that kind of detailed study of constructing real number systems, okay. In what we plan to do is that we shall just list some properties of the real number system which we shall be using very often, and these are the properties which are called defining properties of the real number system. That is, if you take all these properties together, then there is a way of showing that real number system is the only system which satisfies all those properties. Of course, another way of doing this is that, as I said, you can construct natural numbers by starting from Peano axioms. Similarly, one can also construct real numbers starting from axiomatic thing, just state axioms. So our approach is something similar to that. So though we don't call it an axioms, because we are not going to follow that kind of logical rigor here. So what our plan is just to state the properties of real numbers, and at least they should be there together for the record, and those are the ones which we shall be using very often. So to begin with, real number is first of all this non-empty set, okay, we will denote by this, okay, and there are actually, I should say, three sets of properties, okay. I will say first are what are called algebraic properties, okay, and in fact there is another way of dealing with this group of properties. They are also called field axioms, okay. This is one group, okay. Second group of the properties is what is called order properties, okay, and the third group, in fact this third group contains only one property which is known as order completeness property. Order completeness, or sometimes simply called completeness property. and these properties, all of these properties together with this set characterize what is called real number system. Okay. I will come to that discussion also a little later, what is meant by characterizing. Okay. Okay. So first of all let me go to this what are called algebraic properties. What these algebraic properties say is the following. Okay. Algebraic properties or what are called field axioms. Okay. Or what I also call field axioms. It is that first of all there are two operations on the real number system, namely the addition of two real numbers, these and also product of two real numbers. So these are plus and dot, these are two binary operations, and so if you take two real numbers a b, then their addition is defined as this a plus b, denoted by a plus b, and the product is, so since this dot is an operation we should denote it by a dot b, but it is quite customary to forget about writing the dot and just write a followed by b. Okay. So ab. Okay. And these operations satisfy some properties, and those are the ones which are called field axioms. And as we go along this property, you will writing these properties, you will see that there are many other sets also which satisfy these properties, and as we write more and more properties we will see that certain of those sets get eliminated, and real number system is the only system which satisfy all these properties. Okay. All right. First of all let us start with the properties of addition. So the first property is the following. What is, of course all these properties you have already come across in some context or the other, but since we are now discussing real number system, at least once they should be all together, so we are listing that. Okay. So first property is what is called associativity, that is if you take three real numbers and take say a plus b and then add c to it, this should be same as a plus b plus c, and this should happen for every a b c in R. Okay. And this is a property which is called associativity. Okay. Okay, I mean what does this associativity mean in practice? That is, it's a binary operation, so it tells you given two real numbers what is meant by the sum of these two. So suppose you take more than two, what it says, it doesn't matter whether you first add a to b and then add c to the sum, or whether you first add b and c and then add 2 to the a to that sum, whichever way you group these two among these three elements, it doesn't matter. Okay. In fact it is very important when you consider more than three. For example, suppose you write something like this, a1 plus a2 plus an etc. This is something we will be required writing while discussing the series or partials on the series. So that kind of expression will be meaningless unless the operation is associative, because there you have to say how exactly you are grouping the elements. Because of the associativity, it doesn't matter in what way you group the elements. Okay. All right. Now of course these two operations of addition and multiplication, they are defined on many other sets also. For example, the set of natural numbers, integers, rational numbers, etc. Okay. And this first property is there followed by all natural numbers also. So this is, so just suppose real numbers were just satisfying this property, then that doesn't distinguish between R and N. Okay. But now let us say that next property will distinguish between R and N. So there exists an element which is called identity with respect to addition, that we shall denote by 0. There exists a number 0 in R such that a plus 0 is a and 0 plus a is also a. This should happen for every a in R. Okay. And this property says is called existence of identity with respect to this first operation, addition. Now you can see already that this property distinguishes between R and N. Okay. N doesn't have this property. Okay. Though N has this property, it doesn't have this property. Okay. All right. Then the next property is what is called exist. Yeah, by the way, this there are certain things which we will not go into detailed proof of this, because this is something you also learn in many other places. The axiom itself does not say that the identity element is unique. Okay. There is this 0 element is unique, but there is a standard way of proving that once you assume these two properties, then it can be proved that there exists only one element satisfying this property, and hence we can call the identity. Okay, the identity. Okay. All right. Similarly, now we shall say that given for every a in R, we will say that there exists b in R such that a plus b is equal to 0 and b plus a is also 0. Okay. And this is what is called existence of inverse with respect to the addition. Okay. Again, as a similar comment with respect to identity, I mean, I have not stated here that this element b should be unique. Okay, but you can prove. Okay, there are standard ways of proving that. Okay, I will not go into that kind of proof because something like this we will learn in algebra also. Okay, so this element b is unique, and so we can denote that, we can use a notation for this, and the standard notation uses this minus a. Okay, we shall denote this b as minus a, called the additive inverse of a. Okay, and as you know, any set with one binary operation which satisfies these three properties is called a group. Okay, and so I could have just said simply say that R plus is a group. Okay, but again, as I said, that is not something that is something special about R. There are many other groups. Okay, other than R. Okay, and there is one more property, that this group is what is called commutative or abelian group, that is a plus b is equal to b plus a for every AB in R. Okay. Okay. Coming back to my comment about natural numbers, we have seen that a natural number satisfies only the first properties. Okay, it does not satisfy any of this. Of course, it satisfies this. Okay, but it does not satisfy any of these two properties. But if you take the set of all integers, or if you take the set of all rational numbers, it satisfies all these properties. Okay, it satisfies all these properties. So these properties distinguish between R and N, but yet don't distinguish between R and Z or R and Q. Okay. All right. Or for that matter, R and C. Even the complex numbers will satisfy all these properties. Okay. But our idea is that once we write down all these properties, we want to say that a real number system is the only system which has all these properties. Okay. All right. Next, now this is about the operation properties of this first operation. Now let us look at this second operation. Okay, that is also associative. Okay, so A into BC, this is same as AB into C for all ABC in R. Okay, again this is same as, this is called associativity of this second operation. Okay, and the same comments here. Okay, so I will not go into details of that. Okay, then we also want to say how these two operations are related to each other. Okay, that is, suppose you take three real numbers and suppose you take a and multiply that by b plus c. Okay, then this should be same as ab plus ac. Okay, this should be same as ab plus ac. Again, this should happen for all abc in R. And this property is described by saying that multiplication is distributive over addition. Okay, so this is called distributivity. Okay. And perhaps many of you know that any set which has two operations and which satisfies these 6 properties is called a ring. Okay, that is called a ring, and R is one example of a ring. It is not a unique ring. Z is a ring, Q is a ring. There are so many other examples of rings. Okay. All right. Then, but this ring R has some extra properties, namely that it is also commutative ring. Okay, it is also that is the second operation is also commutative. So AB is equal to BA for every AB in R. Okay. Again, this also is there, that property is also there with Z. Okay, Z is also a commutative ring. Okay, then not all, by the way, not all rings are commutative, there are well known examples of non-commutative rings. Then not all rings have identity element with respect to the second operation, but the second operation also has identity here. So that element, as you know, we will call denote by 1. There exists element, let us say 1 in R, such that 1 into A is equal to A, and that is same as A into 1 for every A in R. Okay, so that is a commutative ring with identity, and again the same comment about this identity, we can show that this identity is unique. Okay. Now we shall look for something similar to this, okay, just as we had talked about the inverse with respect to this operation, similarly we want to say something about the inverse with respect to the second operation, and we cannot simply imitate this property here, we cannot say that every element has an inverse, but every element other than that 0, which is identity of the addition, that has an inverse. Okay. So that is the last property in this field axioms. Okay, for every A in R with A not equal to 0, we can say that there exists B in R such that AB is equal to 1 and BA is also equal to 1. Okay. And as I said about the additive inverse, in a similar way this B is called multiplicative inverse, and in a similar way we can show that this multiplicative inverse is also unique. Okay. Given A, there exists only one B which satisfies this property, and hence we can devise some notation for this. Okay, and that notation, as you know, is 1 by A, 1 by A or also A inverse. Okay, that is the notation for the multiplicative inverse. You can see that this last property is not true about Z. Okay, this last property is not true about Z. Okay, right. So already we have distinguished R from N and Z. Okay, we have not yet distinguished it from Q. Okay, but let's see. Let's do it further. Okay, so all these properties together I could have described in just simply one sentence by saying that this R plus dot is a field. Okay, okay, that is why those are called field axioms, and again field is one of the algebraic structures which we will learn in algebra. But I prefer to write down in all details because these are the properties that we shall be using in subsequently. Okay, so that is about this algebraic property. So this is over now. Okay. And so what are the sets with which we could distinguish R using algebraic properties? N and Z. Okay, but Q and C will have all these properties. Those are all, and not only that, there are several other fields also. Okay. So now let us go to the second group of properties, namely this order properties. Okay. All right. So not only that R is a field, but it also has one more property, that namely there is an order. Okay, there is a natural order defined between real numbers, and that order is what we define as less than or equal to. So first of all, less than or equal to is a, okay, for the time being let me simply say partial order on R. Okay, less than or equal to is a partial order on R. Okay, satisfying the following. Okay. In fact, I could have said here itself a total order, but let us go in systematic way. Okay. First of all, this partial order is a total order. Okay, that is given any two A and B in R, either A less than or equal to B or B less than or equal to A. Okay, so we can say that this less than or equal to is a total order. Okay, let me again recall what does this mean. That is given A and B in R, given any two real numbers, A is less than or equal to B or B is less than or equal to A. Okay. Then what we also want to do is to relate this order with respect to these algebraic operations. Okay, we want to know what is the connection between these order relations and these binary operations. Okay. So in other words, what we want to say is that suppose you are given two real numbers a and b, okay, and suppose a is less than or equal to b, and suppose you add some real number to both, okay, then is that order preserved, okay, right, and that is what we should naturally expect. Okay. If the order has to have some relationship with the algebraic operations, some of these properties are natural to expect. Okay. So let us say if a b belongs to R with a is less than or equal to b, then a plus c is less than or equal to b plus c for every c in R. That means addition of some real number does not change the existing order between the two real numbers. Okay. If a is less than or equal to b and to both of those numbers you add some real number, the sum of a plus b will also remain less than or equal to sum of b plus c. Okay. Okay. But you can see that something like that is not true about the multiplication. Okay. Right. Suppose a is less than or equal to b, and if I multiply both of these by some number, let us say alpha, then you cannot in general say alpha a less than or equal to alpha b. Okay. But we can say that in some extra condition, and that is when alpha is bigger than or equal to 0. Okay. So we can say that let me write that if AB is belong to R and let us say 0 less than or equal to alpha, 0 less than or equal to alpha, then alpha times A is less than or equal to alpha times B. Okay. Okay. Now any field on which such an order is defined, okay, and which satisfies these three properties, okay, it is called an ordered field. Okay. So I could have simply described all this 9 plus this 12 properties in simply one sentence by saying this, that R plus dot less than or equal to is an ordered field. Okay. All right. Okay. All right. It is a very well known property. I mean, those of you who have done a course in complex variables, okay, there is one of the first thing that is proved in many of the complex analysis books, that it is not possible to define any order on the set of complex numbers which satisfies these three properties. Okay. So complex numbers is a field, but it is not an ordered field. Okay. So this is what distinguishes between R and C. Okay. So for till now what we have distinguished between R and N, R and Z, and R and C. Okay. But still rational numbers remain. Rational numbers satisfy all these properties. Okay. Okay. So R plus is also an ordered field. Q plus dot less than or equal to is also an ordered field. So the question is, what is it that distinguishes between R and Q? It is this last property, what is called order completeness property. Okay, and we will come to that property little later, but before that I want to say a few things about this order relation. Okay. Some of these things we have already discussed. Okay. Once there is some partial order in any set, you can talk of what is meant by saying that a set is bounded above, what is meant by saying that an upper bound, least upper bound, and all those things. Similarly, what is meant by saying that lower bound, greatest lower bound, or what also called infimum, etc. Okay. Then there are other notations. For example, we also denote that is A less than or equal to B. This is basically same as saying that B is bigger than or equal to A. Okay. So this order relation is nothing but basically reverse of this. Okay. It's basically saying the same thing but using this different notation. Since it is also very popular, we will mention it because it's also quite customary to use this. Okay. And also similarly, what is meant by saying that A strictly less than B or B strictly bigger than A. Again, as we have seen earlier, this means A is less than or equal to B, but A is different from B, and similarly there. Okay, right. So what we can do is that we shall we shall also say that those numbers, let us say suppose 0 is less than or equal to x, okay, right, then as we know such a number is called a non-negative number, okay. So we will say that x is non-negative, okay, okay, and if 0 is strictly less than x, then such an x is called a positive number, okay. And similarly what is meant by negative, if x is less than 0 it is called negative, if x is less than or equal to 0 it will be called non-positive, okay? It will be called non-positive. And we shall also frequently use this notation r plus, either this or some books also use this super, okay, r plus, okay. Let us also, this is more popular, let us see this, okay. This is set of all x such that 0 less than or equal to x, that is set of all non-negative number, okay. By the way, this real number system is also called real line, okay. Reason being, you can identify each real number with a point on a straight line, okay. That is, usually we look at this as a real line, and suppose you take this number as 0, then this part is what is r plus, okay. And similarly this part will be denoted by r minus, okay, this part will be denoted by r minus, it is set of all non-positive real numbers, okay. Then while we are at this discussion of this order properties, there is one more important function that we shall come across very often, which define the real numbers and which depends on the order, and namely absolute value function, okay. Okay, I think I will continue here, okay. Okay, let me write this absolute value function. Absolute value, or maybe you are also used to call it modulus, okay, absolute value function, okay. It is denoted by this mod, it goes from r to this r plus, okay, and we denote it by, define it as follows, mod of x or absolute value of x, this is defined as x if x is bigger than or equal to 0, okay, and this is equal to minus x if x is less than 0, otherwise, I mean, okay. Because of this total order property, any x should be either bigger than or equal to 0 or less than or equal to 0, right, okay. If it is different from, so these two possibilities cover all x, okay. So that is a function on x, okay. And then it is fairly easy to prove some of the well known properties of this absolute value function. One is this, that is absolute value function is always bigger than or equal to 0, okay. This is 0 for all x in R, and this becomes 0 when it will be 0 if and only if x is 0, right, there is no other possibility, okay, because x is to be 0 or minus x to be 0, in both case it means x is 0, okay. So and x mod x or absolute value of x is 0 if and only if x is equal to 0, okay. And second property is the following, absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y, okay. And this is true for every xy in R. In fact, this property and properties like this we shall come across very often in this course. This property has a well known name, it is called triangle inequality. Can you see why it is called triangle inequality? right. I mean basically it says that if x and y represents two sides of the triangle, and if the third side is represented by x plus y, then it's then the length of the third side is less than or equal to sum of the length of the other two sides. So that is what it is, and this is something we shall come across very often in this course. Okay, all right. How does one prove this? Well, we have to make various cases. Okay, for example, suppose x and y both are 0. Okay? Sorry, suppose x and y both are bigger than or equal to 0. Then mod x plus y is x plus y, mod x is x, mod y is y. Okay, so both sides become x plus y. Okay? If both are negative also, same thing. So we'll have to similarly consider various cases. Okay, what happens if x is positive, y is negative, x is negative, y is positive, etc. Okay, consider there are 3 or 4 possible cases, and in all, and basically you just verify that in all these cases this inequality is true. Okay, and similarly we should also know what is the relationship with this absolute value function with respect to the product. Okay, so and that is even simpler. It is absolute value of xy is same as absolute value of x multiplied by absolute value of y for every x and y in R. Okay. Okay. Now let us now go to this last property, namely property of what is called order completeness. Okay. When we discuss partially ordered sets, we discuss what is meant by set being bounded above, what is meant by upper bound, what is meant by least upper bound. Okay, but we did not say that every set which is bounded above it has to have upper bounds. Okay, but it may or may not have least upper bounds in an arbitrary partially ordered set. Okay, whenever that happens, that is called order complete. Okay, right, and this real number system has that property. What is the property? That every non-empty subset of R which is bounded above has a least upper bound. Okay? Has a least upper bound. Okay, it is also sometimes called LUB axiom. Okay, it is also called LUB axiom. Okay, that is every non-empty subset of R that is bounded above has a least upper bound, or what we also call supremum. Okay, and this is a property which distinguishes real number system from the rational number systems. Okay, we can show that rational numbers don't have this property. One can easily construct subsets of rational numbers which are bounded above but which do not have least upper bound. Of course, by that we mean least upper bound in rational numbers. Okay, least upper, because rational number is also a subset of R, so obviously least upper bound will be there as some real number will be a least upper bound. Okay, but that is not what we are looking for. Suppose you just take the set of all rational numbers, then that does not have this order completeness property, which means you can find non-empty subsets of rational numbers which are bounded above but which do not have least upper bound. Okay, we shall come to that kind of examples little later. Okay, by the way, as I have said here, any field which also has this order and which satisfies is called an order field. Okay, and if it also has this additional property of order completeness, it is called complete ordered field. Okay, so what we have said is that R plus dot less than or equal to is a complete ordered field. okay. And I wanted to say further that this is a property which characterizes the real number system, okay. It means that this is the only complete ordered field, okay. What does it mean? You have already heard of what is meant by what is called an isomorphism, okay, between groups or between fields, okay. That is, those are the bisections, those are the maps which preserves the algebraic operations, okay. So similarly one can talk of isomorphism between the two fields, okay. Suppose you are given two fields, there will be a bisection such that addition here is preserved and similarly multiplication is also preserved, okay. When it is an ordered field, we will also expect that an order is also preserved, okay, that order is also preserved, okay. So what this means, what I want to say is that if you take any other completely ordered field, then that will be isomorphic to this, okay. That is, in that sense, this is a unique completely ordered field, okay. Alright, let me just state that more precisely, that is, let me state that as a theorem, okay. If R, let me use some other notations, okay. Let us say R prime plus prime, say dot prime, and let us say less than or equal to prime, okay. Suppose this is a complete ordered field, that means this is a non-empty set, these two are binary operations, this is a partial order satisfying all these things, all these properties which were written so far, okay. If that happens, then this must be basically same as R, okay. This must be basically same, that means what, I mean you may give different labels to the elements, you may give different notations to the operations, but they are essentially the same, okay. To write that in a precise mathematical language, we use what is called language of isomorphism, okay. Then we can say then there exists f from R to R prime such that f is a bisection and first property is f of x plus y is same as fx, this plus prime fy, okay. Plus prime is this operation here, okay, for all xy in R, okay. And similarly for the product, okay, f of xy is equal to fxy again for every xy in R, okay. If it had satisfied only these two properties, we would have called it isomorphism, okay. That is, it means it preserves the algebraic properties. Of course, if it satisfies only these two properties, it is called homomorphism, but since it is a bisection, that is called isomorphism, okay. Anyway, that is not very important. Yes.
Alpha into f of x is equal to
Yeah. It should be fx, then this dot prime fy, right, fx, that's right, okay. Now it's okay. And similarly we have the order is preserved, okay. That is, if you take two elements x and y, and if x is less than or equal to y, then fx less than or equal to prime fy, okay. So third property is this: if x y belong to R with x is less than or equal to y, then fx this less than or equal to prime fy. That means addition is preserved, multiplication is preserved, and the order is also preserved, okay, and it is a bisection. That means as such there is no difference between this and this, okay. So in that sense this is a unique, completely real number system is the unique only complete order field, okay, and that is the one, this set of properties distinguishes real number systems from every other system, every other number system, okay. We shall not go into the proof of this because this is somewhat lengthy, okay, but those of you who are interested, I can give a reference. Okay. You can see the proof of you can see a proof of this theorem in that book. Okay. In fact, some of these things about the set theory also have followed a treatment in this book because it is slightly better than other books. Okay. Book authors are Ali Prentice and Birkinshaw. Principles of Real Analysis, that is the title. Principles of Real Analysis. In this book you will find a detailed proof of this theorem. Okay. Okay. One more thing, as we have said, this is an axiom, that is the most important axiom of the most important property of the real number system, and in fact whatever we need to prove about real numbers, most of the well known properties of real numbers or subsets of real numbers follow from this axiom, either directly, or what happens is that we use this property to prove some theorem, then that theorem to prove something else, and that to prove. So suppose we simply trace back, we can always trace it back to this particular axiom. In fact, this is something that is brought out very clearly in an article. Yesterday I mentioned about Professor Kumaresan. Okay, Kumaresan, he has written one more article about this. Now it is title is role of LUB axiom. Role of LUB axiom in real analysis. This is an interesting article. It gives a detailed account of various properties of real number system and various subsets of real numbers, and how those properties follow directly from this LUB axiom. Okay. Now let us see some of those things now. Okay. There are a few things which I have already mentioned. Once we know that least upper bound exists, okay, then it is clear that the least upper bound is unique. Okay, least upper bound is unique. Okay. All right. Now whatever we can say about the once we assume that least upper bound exists, we can similarly say that if a set is bounded below, then it will have a least upper, it will have a greatest lower bound. Okay, that will follow from this, right? Okay, so we can say that every subset of R, every of course non-empty subset of R, every non-empty subset of R, every non-empty subset of R that is bounded below, has a greatest lower bound, okay, or which we had written GLB, greatest lower bound, or infimum. Okay. In fact, one can show that these two things are equivalent. Okay. That is, if you assume this, you can prove this, and if you assume this, we can prove this. Okay, right? And the whole idea is that the axioms about the order that we wrote here. Okay, various axioms. For example, we said that if A is less than or equal to B, then this implies A plus C is less than or equal to B plus C. Okay, and similarly, if alpha A is less than or equal to alpha B for all alpha bigger than or equal to 0. Okay, using these you can prove the following, that is, suppose you take say two numbers x less than or equal to y, suppose you take two numbers x less than or equal to y, then this is equivalent to say that minus y less than or equal to minus x. that's clear. Okay, in fact that follows from those properties. Okay, try to prove this yourself. Okay, try to prove this yourself from the properties that we have listed. Okay, okay. But let us say, suppose this is clear to you. Okay, suppose this is clear to you. Okay, then suppose a set is bounded above. Okay, let us say A is a subset of R and A is non-empty. Okay, suppose A is bounded above. Okay, suppose A is bounded above. A is bounded above. What does it mean? That there exists some upper bound. Okay, suppose that upper bound is, let us say A is bounded above and M is an upper bound of A. Then this means that X is less than or equal to M for every X in A. Okay, alright. Okay. Now this is same as, now look at, use this. Okay, is this same as saying that minus M is less than or equal to minus X for every X in A, right? Okay. Now suppose instead of A I consider the set minus A. Minus A means what? Take minus X for every X in A. Okay, so I will just use that notation. So suppose I look at minus A, then it is take minus X for X in A. Okay, it's clear. If A is non-empty, minus A is also non-empty. Okay, because if some X belongs to A, minus X belongs to minus X, right? Okay, if A is bounded above, what you can say about minus A? Minus is bounded. Okay, and if M is an upper bound of A, minus M is a lower bound of A. Okay, and so similarly, if something is a least upper bound of A, you can similarly show that that is a greatest lower bound of minus A. Okay, and vice versa. See, suppose a set A is bounded below. Okay, then in the same way you can say that minus A is bounded above. Okay, for example, here if I started with M less than or equal to X, then here we would have got minus X less than or equal to minus M, so that means that minus M would have been an upper bound of minus A. Okay, so you just basically use that and get this from that. Okay, suppose A is a non-empty subset, suppose let us say A is a non-empty subset that is bounded below, then minus A is bounded above, use this to get the upper bound, and minus of that will be the greatest lower bound for this, right? That is it. Or similarly you can go from here to here. So these two properties are essentially the same. Okay, alright. Then I should also make one more comment. This is a technique in the proof which we shall be using very often. Okay, suppose there are two numbers X and Y, and we want to show that X is less than or equal to Y. Okay, suppose we want to say X is less than or equal to Y, and suppose we cannot show it directly. Okay, it's very difficult to show. Okay, and suppose we are able to show this, that X is less than or equal to, or X is less than Y plus epsilon for every epsilon bigger than 0. Okay, suppose we show that X is less than Y plus epsilon for every epsilon bigger than 0. Okay, then will it imply this? Is it clear to everybody? How does, okay, let us see. I think it is not clear to many of you. How does this follow? See, suppose this is false. Okay, suppose this is false. Okay, then what should happen? Y, okay, Y is strictly less than X. Okay, I think let us use this. Okay, that means this is Y and this is X. Okay, suppose this is false, then Y should be strictly less than X. Okay, can I take some positive epsilon such that Y plus epsilon is less than X? For example, I can take epsilon as X minus Y by 2. Okay, suppose I take this number as epsilon, then this Y plus epsilon will be less than X. Okay, right? So here in fact I can even take this. Okay, even if we are able to say X is less than or equal to Y plus epsilon for every epsilon bigger than 0, then that will imply X less than or equal to Y. Okay, right? So this is a technique of the proof which is used very often in real analysis. Okay, right? Okay, then one, okay, so this will imply X is less than or equal to Y. Okay, one more thing. Suppose A is a, let us say A is a non-empty subset, and let us say the number alpha is the least upper bound of A. Okay, alpha is the least upper bound of A. Okay, its a least upper bound means what? Anything less than that is not an upper bound, right? If I take any number smaller than that, then that is not an upper bound. Okay, so which means for so alpha is the least upper bound. This means alpha minus epsilon is not upper bound for any epsilon bigger than 0. Okay, but if something is not an upper bound means what? So there is some element in A which is strictly bigger than this. Okay, so that means there exists x in A such that alpha minus epsilon is strictly less than x, and of course x is less than or equal to alpha. Okay, so if alpha is a least upper bound for every epsilon, okay, we can say that for every epsilon bigger than 0 there exists x in A such that alpha minus epsilon less than x. Okay, in fact this part is trivial because once it is an upper bound, x is less than in that we are not saying anything new. Okay, but this is important, and this is what we shall be using in several proofs. Okay, see if alpha is an upper bound of A, then given any epsilon you can find some number in A which is strictly bigger than alpha minus epsilon. Okay, and a similar statement you can make about the greatest lower bound. If a greatest lower bound exists, any number bigger than that will not be a lower bound, so you can always find a number in A which is strictly less than that. Okay, I will not go to that statement you can write on your own, but this is something which we shall be using very frequently in several proofs in real analysis.